Okay, let's unpack this. We're diving deep today into a part of mathematics that feels both incredibly concrete, think tangled strings, and incredibly abstract. It's the world of knots and tangles.
And while untangling your headphones is one thing, telling apart two complicated mathematical knots or tangles is surprisingly hard. It's a core problem in topology.
Right.
And mathematicians have developed these intricate tools called invariants to try and solve it. These are mathematical properties you can calculate from a knot or tangle that don't change if you just wiggle the string around without cutting it.
Right. You want something that captures the essential knottedness or tangledness. And over the years, these invariants have become incredibly sophisticated. We've seen the rise of powerful tools like the Jones polynomial.
Which really emerged from ideas in physics, actually, quantum mechanics.
Exactly, which led to a whole family of quantum invariants.
Exactly. And the HOMFLY polynomial is another major player in that family. For a while, these polynomials were the cutting edge, giving us numbers or, simple algebraic expressions.
But the quest for more detailed information led to an even deeper idea, categorification.
Categorification. Yeah.
So instead of getting a single polynomial value for a knot, you lift it up to something richer, an algebraic structure called a homology theory.
Right. Think of it like getting a complex musical chord instead of just a single note.
That's a good analogy.
These homology theories, like Kovanov homology or Kovanov-Rosansky's HOMFLY homology, they give you layers of information, often with multiple gradings, allowing you to distinguish even more subtle differences between knots and tangles.
A more powerful lens, basically.
Precisely. It's a more powerful lens. And our deep dive today, guided by this fascinating research paper you've shared, is specifically focused on a particularly complex flavor of this understanding colored HOMFLY homology.
And not for all knots and tangles, right?
No, for a special structured class called rational tangles.
Okay, so we've got the complexity of coloring, the power of categorification, and a specific sort of well-behaved playground, rational tangles.
That's the setup.
Our mission is to explore this paper and pull out the essential insights for you, our listener, who's maybe familiar with the general landscape but wants a shortcut to understanding this cutting-edge research.
Let's set the scene then. What do we actually mean by colored?
Good question. It adds another dimension. Instead of treating every strand in a tangle identically, you label them or color them with specific mathematical objects.
Okay.
In this paper, they're using objects related to the Lie algebra SLN specifically, the exterior powers of its fundamental representation. So a strand might carry color 1 or egg or ish.
Like giving different threads different mathematical properties based on some underlying algebra.
Exactly.
And adding these colors makes the invariants even more powerful in theory, but also much, much harder to compute and understand. The paper makes it clear, colored HOMFLY homology is still largely mysterious, even for relatively simple knots.
So that's the challenge, and that's why focusing on rational tangles and links is such a smart move, as the source points out.
Right. There's sort of a mathematician's friend in this complex landscape. Rational tangles have this beautiful, simple, recursive structure.
Recursive.
Yeah, you can build any rational tangle by just repeating two basic twist operations. This makes them much more amenable to calculation than, arbitrary tangles. Their simpler structure suggests they might be the key to unlocking understanding for the more complex colored invariants.
Okay, so rational tangles are our test subjects because they have this built-in order. And the researchers in this paper aren't working blind. They're guided by a couple of key conjectures that predict surprising simplicity within this complexity.
Right. Let's look at the hopes for this theory straight from the paper. The first one, attributed to Marko Stojic, deals with rational links with two components, where one of them is just an unknot, like a simple circle linked with the tangle.
Okay.
It predicts that if you fix the color on the tangled component, say ging, and simply change the color on the unknot component, say from A to A, the resulting HOMFY polynomial doesn't wildly change.
It doesn't. What does it do?
It essentially just shifts the Q grading in a very predictable way. The formula looks like HPJL, FJLA, SQJ, and TQ. That sole variable captures the shift based on the difference in colors.
Huh. That's fascinating. It suggests the invariance dependence on the color of that simple unknot component is quite constrained and simple.
Exactly. Just a shift based on the difference in color indices, IJ. A simple pattern emerging from something complex.
Okay, what's the second conjecture?
The second conjecture is related to a broader idea of refined exponential growth. It suggests that for a rational knot or link, The homology for a higher color, say Sanjo, might behave surprisingly simply compared to the simplest color AJ1.
How so?
It predicts that after a specific adjustment to one of the gradings, they call it the corrected, Q grading the homology for Shea, written page AL, looks like the homology for the simplest color, but just sort of multiplied by itself J times. Like page A behaves like in some algebraic sense.
Whoa. So the complicated structure for color J is somehow built very simply from the structure for color 1. That really points toward an elegant underlying structure.
Yeah, suggesting these invariants aren't just chaotic messes, even with colors.
So these conjectures are like beacons, suggesting there's a hidden simplicity.
Exactly, and this paper's big contribution is making concrete progress towards understanding these ideas, specifically by studying the categorified SLN invariants of colored rational tangles. They're building the foundation in the categorified world for these simple objects.
So they're taking the conjectures, which were initially about the simpler polynomial invariants, and looking for analogous behavior in the much richer homology theories, focusing on these well-structured rational tangles.
Precisely, that's the game plan.
Okay, that's the goal in the test bed. How do they actually build and compute with these objects? It sounds complicated.
Well, you have to start with the basics, even in the categorified world. These invariants fundamentally arise from the representation theory of quantum groups, like UQ, SLN. But working directly with that algebra can be very abstract.
Right, which is where the visual language comes in, I suppose. The paper makes extensive use of what they call the SLN spider category, using diagrams called webs or MOI graphs.
Exactly. Think of these as a graphical language for representing algebraic operations on the colored strands. They're diagrams with edges labeled by colors and specific vertices showing how strands merge or split, like little computational rules embedded in the diagram itself.
And these diagrams aren't just random drawings.
Oh no, they obey strict local relations, rules about how parts of the diagram can be simplified or rewritten. These rules come directly from the underlying mathematical structure, the algebra.
Got it. So they encode the algebra graphically.
Yes, those relations are crucial. And standard operations on tangles, like adding a crossing or closing a loop, what they call a cup or cap, are translated into specific webs or combinations of webs. They also have clever ways to handle strand orientation changes using color shifts related to n-k.
And underpinning all of this graphical calculus is a deep result called Skew-Howe duality.
Ah, yes. This duality is really the engine connecting the abstract algebra to the visual diagrams. It provides a fundamental correspondence between the representation theory side and these web diagrams. It's why computations you do with the webs actually mean something profound about the algebraic invariants.
So it justifies a whole graphical approach.
Pretty much. The Rasheta-Contorius invariants we mentioned earlier, the polynomial ones, can essentially be calculated by evaluating specific webs using this framework.
Okay, so that's the decategorified picture webs as a shortcut to calculate polynomial invariants. How do you make the leap to the categorified world, the homology theories?
Right, here's where it gets really interesting and a bit more abstract. In categorification, you replace those single webs, or the maps they represent, with chain complexes of webs.
Chain complexes.
It's not just one diagram anymore, it's a sequence of diagrams, or more precisely, spaces built from these diagrams. These are the chain spaces connected by differentials, which are maps that move you from one chain space to the next in the sequence.
So something like a crossing, which might be represented by, say, a sum of two webs in the polynomial world.
Becomes a whole complex in the categorified world. Perhaps several webs arranged in different chain spaces, with specific maps between them. They use specific known complexes for crossings, like the Tron-Ruquier complex.
Okay, and combining tangle pieces, like stacking diagrams.
That translates to taking the tensor product of these complexes. So you're combining these sequences of maps. The final invariant isn't a single web or polynomial, but this whole intricate chain complex living in a higher algebraic structure, a kind of homotopy 2 category. It contains vastly more information than the polynomial ever did.
Wow. That sounds incredibly complicated to actually compute. How do they approach that for these rational tangles?
Well, they leverage that simple recursive structure of rational tangles we talked about. Remember, you build any rational tangle using sequences of those two basic moves, top twists and right twists.
Right, related to the continued fraction. You gave the T72 example corresponding to 72, built from twists 3-2.
Exactly. So you can break down the construction of the tangle into these simple, repeatable steps. And since computing the full complex, including all those differential maps, is very, very hard,
They simplify.
they focus on a crucial first step, describing the chain spaces themselves. What are the actual building blocks that make up each level of the complex? Forget the maps between levels for a moment. What are the levels made of?
Okay, so what are they made of?
That's right. They identify a specific, finite set of basic objects.
Yeah.
These are particular, relatively simple web diagrams that actually span these chain spaces for colored rational tangles.
Ah, so it's not infinitely complicated.
For a given rational tangle in colors, no. These basic objects are categorized by type. They have names like UP, OP, RI, and so on, based on their shape and a weight related to the colors on the tangle's boundary strands, say I and J.
So instead of the chain spaces being potentially infinite messes of diagrams, they find they're built from these specific finite atoms, these basic objects.
Precisely. And their computational strategy becomes figure out how these basic objects and their associated gradings change when you apply one of those fundamental top or right twist operations.
Like rules for the twists.
Exactly. They derive explicit twist rules that tell you if you start with a basic object, what collection of basic objects you get after a twist, and crucially, how their gradings shift. Remember, these homology theories have multiple gradings like T and Q.
And this is where they find something really elegant, right? Related back to those initial conjectures about simplicity, they discover that the complexity introduced by the large rank n from SLN and the specific higher color I, when using color I along with J, assuming I 8AJ, can be captured remarkably simply.
Yes, this is a major finding in the paper, Theorem 7. They show that the dependence on n and the specific color index I is actually encoded just by two new variables they introduce, AQN and SQIJ.
Wait, so all that complexity just boils down to these two things?
Pretty much. The explicit twist rules they compute depend only on these two variables, A and S, along with the usual Q and T grading variables. The N dependence and the specific I dependence are wrapped up neatly.
That's a significant aha moment. It means much of the complexity associated with the dimension n and the specific higher color just melts away into these simple variables, A and S.
It reveals a deep pattern, a stability.
And this variable substitution proves Theorem 7, demonstrating this clear stability property for the categorified invariants of tangles, which really echoes that first conjecture about how changing the color on an unknot just leads to a simple shift.
Exactly. It's the categorified analog for tangles. And the tool they use to track the counts and gradings of these basic objects after applying the twist rules is a multivariable Poincare polynomial.
Okay, what's that?
It's basically a formal sum. It keeps track of how many basic objects of each type you have, weighted by powers of T for the homological grading shift, Q for the Q grading shift, and now the new variables A and is based on their gradings as determined by the twist rules. It's like a blueprint of the chain spaces.
So the twist rules compute this detailed polynomial blueprint. But the paper doesn't stop there, right? It offers a totally different way to look at this, almost intuitive.
Yes, this is section 4, the geometric model. It provides an alternative visual perspective that's quite powerful and maybe more intuitive for some people.
Okay, I'm intrigued. What's the picture?
The core idea is to represent the rational tangle not just with those abstract webs, but with a planar diagram involving a single curved arc, let's call it alpha, and two vertical lines crossing it.
And the construction of the rational tangle using twists, how does that fit in?
That corresponds to simple geometric manipulations of these vertical lines. You build the diagram inductively by bending the vertical lines, sort of mirroring the top and right twists in the tangle construction. And crucially, they identify specific special points where things happen in this geometric diagram. They call them X plus X and Y.
Okay, so we have this geometric picture with an arc, lines, and special points. Where do the complex algebraic objects, the generators of the colored HOMFLY complex, show up here?
This is where the geometric view really shines. They show, in Theorem 42, that the generators of the complex, the things that make up the chain spaces for a specific weight H and specific colors H with IJ, are identified geometrically with sets of intersection points.
Intersection points? Between what?
Between parallels of those two vertical lines and the curved arc alpha. You imagine taking J parallel copies of the vertical lines in total, some weighted and some unweighted JH, and the specific J tuples of points where these parallels hit the arc. Those correspond one-to-one with the algebraic generators.
Wow, so the abstract basis elements, the generators, are just specific sets of points on an arc. That's a huge simplification in perspective.
It really is. And the paper gives rules for how the relative gradings between these generators are determined purely from the geometry.
Okay, how did that work?
Precisely. They have geometric rules, also in Theorem 42, for calculating the grading difference between two sets of intersection points. two generators. One rule applies when the sets differ by just one point moving, essentially, but staying at the same overall weight. The grading difference here is related to geometric winding numbers, or graded intersection numbers.
Winding numbers.
Yeah, of simple regions, simple disks in the diagram with those special points, x plus L, x, y, and also with the other intersection points. The contribution to the grading depends on what the boundary of the disk encloses.
So the algebraic grading shifts that showed up in the twist rules now have a geometric explanation based on which special points or other intersections are seen by certain regions in the diagram.
Exactly. And crucially, this is where the A and S gradings appear geometrically. For instance, how a disk interacts with x plus might contribute a factor involving A and S. How it interacts with other points contributes Q factors.
Okay, that's one rule. You mentioned another.
Yes, another rule describes grading shifts when generators are related by what they call a simple slide. This geometrically corresponds to sliding the innermost vertical line across one of the special points, y, x, or x plus. Each point you slide over contributes a specific, predictable grading shift involving T, Q, and sometimes A or S.
So the geometry dictates the grading entirely. This geometric picture provides deep insight into the structure of the generators and their gradings. And this is where Theorem 9 comes in, offering a geometric perspective on that second conjecture, the exponential growth one.
That's right. Theorem 9 uses this geometric setup to clarify how the generators for higher colors D are structured. It shows they really do look like J-tuples of island-like generators geometrically. And it explains how their gradings combine. The A, S, and T parts of the grading just add up nicely when you combine the arrow generators to form a K generator. The Q grading behaves a bit differently. It splits.
So the additive behavior for A, S, and T in the geometry provides strong support for the kind of structure predicted by conjecture 2.
Exactly. It gives a visual, intuitive reason for why that conjecture might hold.
And you mentioned earlier that the geometric idea of simple slides connecting generators feels like it's hinting at the differentials in the complex, the maps that connect the chain spaces.
Absolutely. While the paper focuses on describing the generators, the chain spaces, the way these generators are related by simple geometric moves strongly suggests that the differentials themselves might have a beautiful geometric description, perhaps corresponding to these slides or related paths. This is a key direction for future work hinted at.
This whole geometric model feels like it could connect this specific area of knot theory to other fields, maybe physics or geometry.
It definitely opens doors. The geometric picture, as the authors note, bears structural similarities to diagrams and models used in areas like Floer theory and symplectic geometry.
Are there specific connections mentioned?
Yes, they explicitly mention resemblances to models like Bigelow's grid diagrams for the Jones polynomial and Manilescu's work on symplectic Kovanov homology. They're careful to point out the differences, too. They're dealing with rational tangles, not braids, SLN, not SL2, and so on.
But the similarity is suggestive.
Very suggestive. This geometric connection is really exciting because it hints at a potential model realization, a connection to geometric theories like symplectic geometry or string theory for these SLN-linked homologies, at least in the case of rational tangles.
And there's a concrete link to another established invariant too, right? Not just a hint.
There is. Corollary 10 is a nice, solid result showing that the HOMFLY complex of a rational tangle, when you actually compute its homology, computes something known, the link Floer homology of its denominator closure.
Denominator closure.
It's a way to turn the rational tangle into a specific two-component link. So this new categorified invariant is shown to compute a known and important invariant from Floer theory in that case.
Very cool. And the paper also circles back to the original decategorified conjectures, providing proofs for conjecture 1 at the level of the HOMFLY polynomials.
Yes, they nailed down that first conjecture for the polynomials. They used two methods for that proof. One relies on evaluating the web diagrams, connecting back to the building blocks we discussed earlier.
And the other?
The other uses the classical skein theory of the annulus, and that skein theory approach leads them to define something interesting, the color-stable HOMFLY polynomial, which they call PSKLU.
Color stable, that sounds promising. Connected to conjecture 1 again.
It is. It's a three-variable polynomial. It depends on A, S, and Q. That specifically captures how the reduced colored HOMFLY polynomial of a link L with an unknot component U changes only based on the color of that unknot, encoded in S and Q.
And there's a neat surprise here, too, a connection to something really classical.
Yes, this is Theorem 65, Lemma 66. They show that when you evaluate this new color-stable HOMFLY polynomial as specific values. You set A1, SUV, and QV. You recover the classical multivariable Alexander polynomial of the link L.
Wow, the Alexander polynomial. That's one of the oldest not invariants.
Exactly. It's another connection demonstrating that this modern, sophisticated framework for colored rational tangles links all the way back to fundamental, well-known invariants. They even note the geometric algorithm can be adapted to compute this Alexander polynomial calculation too.
Wow. So this single research paper framework for colored rational tangles connects quantum invariance, categorification, a complex combinatorial structure via webs and twist rules, an elegant geometric picture with arcs and points, hints at deep connections to Floer theory and symplectic geometry, and even ties back directly at classical invariants like the Alexander polynomial.
It's a remarkable synthesis of ideas from different areas of mathematics, really pulling things together. They even briefly compare their invariants to those arising from Lie superalgebras, suggesting the potential for even broader connections down the line.
What a fantastic deep dive. We've navigated the complex world of colored HOMFLY homology for rational tangles, guided by this paper. We saw how abstract quantum invariants are lifted to powerful homology theories through categorification.
How the structure of the resulting complex can be understood through combinatorial twist rules governing these basic object building blocks.
And how a geometric picture provides surprising intuition and computational power, turning algebra into points on an arc.
And the key takeaways for you, our listener, are those insights into conjectures 1 and 2, the surprising stability and structure predicted for these sophisticated invariants, especially for rational tangles. We've seen how the variables A and C's neatly capture crucial dependencies on the Lie algebra dimension n and the specific colors involved.
And that geometric model, visualizing generators as intersection points and gratings as winding numbers, that's a powerful shift in perspective, really linking topology, algebra, and geometry in a concrete way.
Plus, the exciting connections unearthed, not just hinting at Floer theory, but landing squarely back on the familiar territory of the Alexander polynomial.
It shows just how interconnected these seemingly disparate areas of math really are.
It really makes you think. The geometric model gives us generators as points and gratings as geometric counts, like winding numbers. The paper strongly hints that maybe the differentials, the maps connecting the chain spaces, also have a purely geometric description, maybe as these simple slides or related paths. If the entire complex generators, gratings, and differentials can be described geometrically like that, maybe using these intersection points and paths between them, what does that tell us about the true fundamental nature of these abstract algebraic invariants?
What other powerful mathematical structures developed purely algebraically might have hidden geometric lives just waiting to be discovered? That's definitely something to mull over.